we're going to jump into section 2.2 here, which is about instantaneous velocity. Before, we drew a graph that sort of described stopping and going on the way to get to the Kennedy Expressway, which was 3 kilometers away. We found that if we took the distance, delta x, and divided by the time, not delta y, that would be delta t, we could determine the average velocity, which in this case we determined to be 3 kilometers divided by 0.1 hours, which was 30 kilometers per hour. But it didn't really explain all the intermittent or intermediate. So we're going to look at instantaneous velocity, which means your velocity at a particular instant. So we're going to look at a graph that represents an airplane going down a runway. So it starts from 0, at time 0, it's not moving, but the engines kick on, and it's, in this particular case, it covers the first 100 meters in about 5.5 seconds. So we have first 100 meters in 5.5 seconds, the second 100 meters in 2.5 seconds, so from here to here in 2.5 seconds, and this last 100 meters in 2 seconds. So it's covering each 100 meters faster and faster and faster, which means the velocity is changing. If we take the average velocity, we say it covers 300 meters in about 10 seconds, or 30 meters per second. If we look at each of these individual average velocities, break it down a little bit, we find that it covers the first 100 meters in 5.5 seconds, which is an average velocity of 18.2 meters per second. The second 100 meters in 2.5 seconds. If we divide 100 by 2.5, it gives us 40 meters per second. And the last 100 meter interval in 2 seconds, which is 50 meters per second. So you can see the average velocities keep increasing because the slope keeps getting steeper and steeper and steeper. But notice, this average velocity for the entire interval is somewhere down here in this range. As the slope of the line gets steeper, as we then squeeze this down a little bit more, we get a better idea of what its velocity is in between these intervals. Now, this is a parabola, and the graph of this parabola is x, the y-axis, equals t squared times 3, or x equals 3t squared. Now, we use a little trick of mathematics and calculus to actually figure out what little tiny portions of this graph are like. And it's called taking a derivative. And so the derivative of a function equals, in this case, function f dx divided by over dt. So in order to calculate the derivative, we take the exponent, multiply it by the coefficient, and reduce the exponent by 1. So 2 times 3 is 6, and 2 minus 1 is 1, so this would be 6t. So by plugging in any time between 0 and 10, we can figure out exactly how fast this thing was going. Pretty cool. We can also take, so the velocity is the derivative of the x graph, x in terms of t. Now, in calculus, you're going to learn this as the limit as delta t approaches 0, meaning as the t gets smaller and smaller and smaller, when you get it down to about 0, there will be a little finite slope there. So the limit as delta x goes to delta t equals dx over dt. Now, dx dt means the big one. That means like the slope between 2 points. If we shrink down the big delta into what we call tiny deltas, this is a capital D, that's a lowercase d, we get a very, very small interval over which we are calculating the velocity. And that essentially gives us the instantaneous velocity. How to take a derivative, again, to make this a little more clear to you, is that we have a function that describes the position of the airplane. What we do then is we multiply b times a to get, and then subtract 1 from the exponent. So b times a we see here, b minus 1 we see right here. This also works with lower power. So here we have ct, but ct by itself means to the first power, so 1 times c equals c. And if we reduce t to the first down to t to the 0, anything is t to the 0 equals 1, so therefore we don't need to put a t here. In a practical sense, with numbers plugged in now, if we have a function x equals 7t cubed minus 3t squared plus 7t minus 6 minus 6, the derivative then is 3 times 7 equals 21. Subtract 1 from 3, we get 2, so 21t2. 2 times 3, 2 times negative 3 is negative 6, and we subtract 1 from t to the second, gives us t to the first, and then this guy is t to the 1, we subtract 1 from it, it becomes t to the 0, and so just the 7 comes down. 1 times 7 is 7, and t to the 0 is 1. And then this was just a plain 6 here, and that doesn't do anything, because there's no t next to it. So that's how we calculate derivatives. And we're going to do an example in the next video.